moving into this new chapter, which is largely on aqueous equilibria. So there's all kinds of various topics we can get in with that, mostly acid-base chemistry and solubility. And we're also going to talk about complex ion equilibria. But I wanted to start this chapter with a very brief intro video talking more about this ocean acidification via carbon dioxide. Okay. And we talked about this before, but I really wanted to get into this and look at some of the data. And the book does a really nice job describing this in section 16.1 if you want to read further. But I'll summarize briefly here. So if we look back at the historical record, and note, this is in thousands of years before present. So like, for example, that 800, that's 800,000 years ago. And this is a determination of atmospheric CO2 concentrations, which is mostly done through ice core sampling. Atmospheric air, so the air we breathe, can get trapped as bubbles into ice and water and freezes over time and adds up, piles up as the ice builds and builds. So scientists have gotten really good at digging down into those ice cores, and they can not only determine the age through isotopic analysis, which we'll talk about at the end of the semester, but then they can also see what the composition of the atmosphere must have been like. Okay, and as you can see, it's quite detailed. This is a remarkable set of measurements that have been done. And this scale right here, notice that says ppm. So recall from Chem 109, that stands for parts per million. And so, for example, if you have 1 ppm for this gas phase measurement, that means 1 molecule of CO2 out of 1 million molecules of air, right? So 1 part per million means 1 out of every 1 million. So you can see throughout the historic record, CO2 is kind of oscillated between roughly 200 and 300 parts per million, which does sound like a very small concentration, but because CO2 is such an efficient greenhouse gas, it doesn't matter that it's a small concentration. That concentration is actually significant. And throughout history, CO2 has kept our planet at a nice, comfortable temperature, right? It's the Goldilocks planet. We don't want it to be too cold, but we don't want it to be too hot. We want it to be just right. So we actually need this. We need some amount of CO2 in our atmosphere to maintain this comfortable climate that we're used to, okay? However, something interesting happened, I think, as you all are probably pretty familiar with. So I'll point to this point on the graph. That's approximately 1850. And as many of you are aware, that's the start of the Industrial Revolution. And you can see here, even though throughout history, almost 1 million years, CO2 has gone up and down and up and down. As you can see quite clearly, it is shooting way up, much higher than we've ever seen throughout the record. Okay, so this is why it's a concern for us. And of course, as we talked about in the previous chapter, via Le Chartier's principle, as we increased CO2 in the atmosphere, that's gonna, when it gets taken up into waters across the planet, oceans, lakes, rivers, streams, okay, it's gonna push that equilibrium to making more carbonic acid. And as we make more carbonic acid in solution, we know via Le Chartier's principle, that's gonna make more H+. And as we shall see, just a slight increase in H+ in the ocean is a big deal for aquatic life. Okay, so this is just a zoom in of more recent times. So you can see this scale from 1960 to 2020 wouldn't even show up on this graph that's spanning roughly 1 million years. And if you were to zoom in, you can also see there are definitely natural cycles of CO2 where it increases and decreases. But if you look at this highlight here through 1 year, one annual cycle, you can see it kind of increases in late winter into the spring. And then as vegetation comes back and photosynthesis starts taking over, right, there's a lot more vegetation now on the planet that can breathe in that CO2 and decrease its concentration. And of course, as we get back into the winter, and things start shedding their leaves and there's less photosynthesis, then CO2 goes up. However, it's this natural cycle. You can see it does not oscillate by very much. But rather, if you look at the big trend here, this big increase is absolutely due to humans.